Today's talk will be about writing an emulator and the lesson, often kind of painful, that I learned while writing my own one. So basically, what is emulation? Emulation is actually the process of representing via software what older systems usually did via hardware. The reason for doing so are actually many, like often not finding the dedicated hardware anymore. And writing one from scratch is actually fun as hell, but also pretty difficult. Pretty difficult because, well, you have to ask yourselves quite the big number of questions. Some are more, let's say, meta questions, like, for example, at what level should I emulate stuff, whether at system level, at component, or at gate level. Spoiler, don't do at gate level because it's painful. Or the fact that usually as software engineers, we tend always to abstract and abstract and abstract. Well, in this case, we are, let's say, brought to abstract up, but the target is something that is very low level. So there is kind of a mismatch of impedance, let's say, between the two steps. And finally, one of the most important questions is whether actually bugs and quirks that are present at hardware level should be emulated as well. And the answer for that is actually it depends. Probably you want not to emulate a quirk that basically breaks your console, but there are many cases in which a bug actually becomes a feature the moment all the developers found out about it. There are also some more technical questions, for example, and problems. And the biggest one for sure is finding documentation that is coherent, because well, it's hard to find because we are often talking about 30 and more year-old systems. Sometimes it's fuzzy, sometimes it conflicts with what another document says. So also this brings the issue of testing, because testing at this point is, yeah, I can write the unit test and hope that everything will be fine, but it's all based on my assumptions that I read from the documentation. So it is quite a strong assumption to assume that everything will always be correct. And the problem that we have is that usually hardware is really dedicated for that specific device and for nothing else. So basically every time you start completely from scratch. One other, let's say, issue is that you have to cover a lot of edge cases, because really, usually it's a simple architectures, but this means that the devs really got really creative in what they could try to do. And sometimes you have some edge case that you could not expect because no, there's no way that will happen. And of course, now, for the case study, this is what I will be talking about. Actually, it's a very simple system, meaning it has a serial port, it has a system of a chip, which basically means that graphics, the CPU, audio is all bundled together. You have some RAM, some VRAM, and the slot to hold the cartridge. Now, I will give you a hint for what it might be. Yeah, that's the Game Boy, actually. Actually, it's arguably the most successful handheld console ever. It has more than 100 million devices sold from the beginning of its life cycle to its end. And actually, it had this success because it was focused on being cheap, sturdy, and power saving. This actually had all kind of implication. The system is a pretty simple one. It's an 8-bit system and it's entirely memory mapped. This means that the architecture as well is pretty simple. You can see it. Basically, you have, let's say, a central point that is the address space, memory, bus, however you want, the CPU, the PPU that governs the LCD display, and then the rest of the word. So basically, joypad serial all end up being written as bits in memory. Now, having said this, how do you implement an emulator? Well, you usually start from the part upon which everything else depends on, and that's the other space. It's not really that complicated right now, meaning, yeah, you can just have a 64K array of bytes and be done for it. Well, yeah, you can add some functions to write and read memory from it, but nothing more. That's wonderful. How harder can it become? Well, it turns out that this for the CPU, it's again another kind of, let's say, funny beast, meaning the CPU is governed by a clock that runs at 4 megahertz. But since, due to cost and power saving reasons, the RAM is bound at 1 megahertz, it means that we'll never go faster than that. It's, let's say, a normal CPU in the sense that it's right-Endian. It has the usually fetch the code executing mode of operation. And in its, let's say, in a nutshell, it is pretty easy to understand conceptually. You read something from memory, optionally read something more, update internal state or memory. You have, for this, since you have 64K of addressable memory, you have two main 16-bit registers, the usual stack pointer and program counters. The other 8 main bit registers are slightly more complicated in the sense that, yeah, you have 8 of them, but more often than not, you will find them also joined together so that, for example, register B and C, you can see them as being a 16-bit register BC. Now, 2 of them are kind of special. Well, that's the usual accumulator in which all kind of arithmetic operations ends up, and the flags. We have lots of flags, actually, in this device. 4. Of them, we will use only 2 because the other 2 are used internally by a single opcode. And the funny thing is that the F register, the flag register, is actually not directly addressable by the opcodes. Still, the opcodes manage to use an 8th pseudo register that is basically the address of memory that you get when putting H and L all together. So basically, you consider HL as being the address of memory and you use it as a pseudo register. Of course, it will take longer to write and read from it. Now, the opcodes, well, they were not difficult, they were tedious, meaning many of them are just slight variations one of each other. Why this? Because we are on a slow system with little space. So the more information I can cram into a single byte, I can save, and the more time I will have to do something else. Now, there was no way I was going to implement them by hand one by one. So actually, if you, let's say, forget the abstraction of the opcode, there is a nice trick that you can use that is basically how do I say? You consider them as being 8 individual wires. Each wire, when set, will direct the modes of operation in one direction, for example, to the ALU, or to something else, for example, switching registers. They were kind of funny by themselves in the sense that there are some opcodes that makes absolutely no sense. For example, load A into A. Yeah, wonderful, completely useless. Some of them do kind of the same thing with slight variations, and those are the one that punishes you the most because, yeah, of course, add something to one, add the one to something and increase that something is the same operation. Nope, one of them doesn't change the flags, for example. Some of them may also crash the Game Boy directly. Too bad. Going back to address space, well, I kind of lied in the sense that now that we have a CPU in place, we can start playing with it a little bit more. It's not really a simple array of bytes, but actually it is mapped to different parts of the system. So for example, of the 64K, the first 32Ks will be ROM dedicated to the cartridge, well, actually the real ROM on the cartridge. You will have the VRAM on which some tiles will be present, the external RAM, for example, for your save games or whatever, working RAM, eco RAM, system RAM. In the system RAM, it's actually only half a kilobyte big. there is a lot of stuff in the sense that you have all the information about the sprites that you're going to use, some unusable memory, the communication with the external world, meaning a joypad, display, sound, and whatever, and the zero page that is actually a concept, let's say, an area of memory that is way faster to read and write from with respect to the usual RAM, because basically you can take the first byte as being fixed value, so you don't need to read it. Well, then it is fine. It works for Tetris, but fails actually for pretty much everything else. Well, the reason for this is that, of course, as time goes on, people want to cram more and more stuff into the cartridges, which is fine, except that the space that is allocated to the ROM cartridges is always the same. So they needed a way to kind of switch them altogether. What was the solution for this? Well, it is one that obviously irritates me every time that I see it. It's writing to ROM. Of course, you write to read-only memory. Well, it turns out that in the cartridge, that one is one, there is a small circuitry that is dedicated just to this, basically switching ROM and RAM. It's called the memory bank controller. And what it does is that when you try to write some specific values into some specific location of the ROM, this chip will, let's say, intercept the call before it has been done. And then depending on what you wrote into that, you will be able to disable the RAM, for example, to save a power, or switch the ROM bank, the second ROM bank that you're going to use. The first one is always fixed. And well, there are many kinds of them, each with its own quirks, but luckily one thing is that you do not have to implement all of them. I mean, I don't really care if the cartridge has an accelerometer inside. Too bad for them. What is still missing is the graphics. This might range really from complex to nightmarish, depending on how deep you want to go inside the rabbit hole. The display is per se really small. I mean, it's just 160 by 144 pixels, which is fine. And it mimics really well, actually, a CRT, an old CRT. So what happens is that you draw something, then you go back, and so on and so forth, and then you go back. And it actually mimics it so well that you also have some intervals, the H blank and the V blank intervals, that are the green and the red arrows there, in which nothing is written to the display, and so the CPU might try to do something with the graphics there. The only difference is that you can alt putting the pixel inside the display. It's really not like we are used to do right now, that we just swap the frame buffers and then you call it a day. Now, since it's really small, but we have even less space, what happens is that the whole system is tile-based. You have some tile maps, usually 2, but again, you can switch them if you switch the ROM bank in some specific conditions. And there are 3 main components. But the background, which actually is way bigger than the one you expect it to be, because actually what is displayed is just a viewport that is rolling around of the whole system. You have the window, that is this one, that basically completely overrides the background below, and you usually use them for status bar, and the sprites. Sprites, due to hardware limitation, you can have at most 40 of them, sorry. But due to other limitations in a single scan line, well, you can have of them. Sprites are limited to being just 3 colors wide, because the 4th one is always the transparent background. Otherwise, you would have really always the blocky effect that you don't want to really have. Now, who governs all of this? That's the pixel processing unit. It is basically the grandfather of our GPU. And well, it's kind of a sibling of the CPU in our context, in the sense that it runs at 4 megahertz, and this time it's real 4 megahertz. And it has basically owner rights on both the VRAM and the OEM, so basically where all the information about the sprites. So basically what happens is that the CPU, she might try to write and read from those areas, but that's the PPU that will say whether the operation will be successful. Luckily, it's one of the places where you can cheat the most, in the sense that if it gets complicated, you can take shortcuts, of course, but the cost is that some games will have glitches or will not run altogether. Now, how does it work? You have a total of 144 scan lines to really display, plus 10 extra that will mimic the H-blank interval that the real monitor should have. What happens is that at the beginning of each scan line, well, you will look for all the sprites that are supposed to end up in that specific scan line. So basically, it will take always the same amount, and you will need to find the first 10 you're going to grab. Then you start drawing, really physically putting every single pixel. But this is not, even if the width of the monitor is always the same, 160, this actually takes a variable amount of time because the PPU works with a queue, basically. And sometimes, like when you're trying to put a window, you have to flash it, whatever you had before, and that stuff takes time, so unfortunately. Nothing that we can do. Then there is an H-blank in which, again, the CPU might try to do something with the VRAM and the other one, but it's actually very little time. You see, in some cases, since it's depending on the drawing mode timing, you might not have really the time to do anything meaningful. What you're going to do is, once you reach the 144th line, the PPU will kindly provide an interrupt, and then the CPU knows that it can do whatever it wants for a fixed amount of time. And also calculation of how much time will it take, it's always not really that simple. And that's more or less where the point that I reached with my emulator. Now, I had some issues. Basically, one of the issues that I had was basically testing it, because, again, unit test is, it works, it's nice, assuming that the documentation is correct, which is actually a really strong one, again. Found out the hard way. Yeah, you could play the whole games and see if anything weird happens, but don't do that because, again, then good luck finding the bug, because sometimes it's, I should have forgotten to set this flag and this screwed up completely everything. And luckily, there are some kind of source that created some ad hoc ROMs that basically test the system as it is supposed to be, and all the known quirks and bugs that are there. Emphasis is on known, because every time there is something new that pops up, and so they will release a new version. However, since it's a ROM, well, it cannot really interact with you directly. So what they can do, and they usually do, is setting up either on the display of the whole emulator, or if you don't have it, because you're implementing the CPU, you don't have a display right now. What they do is send the data on the serial port, and then you read it every single time. Not the nicest thing, but it works. And for now, that's more than enough. So what will I do with this emulator? I don't know. Well, first of all, right now, I am one of those that take quite the number of shortcuts while implementing the PPU. So I want to go down that rabbit hole and see what happens. Then there's audio, which it's kind of, let's say, not simple, not complex conceptually, but implementing it will be quite the pain, especially since I'm completely tone deaf. So I can do something. I have no guarantees because I can really distinguish a tone from another one. Too bad. One thing is maybe allowing for debugging the Jasmine, so basically create a whole environment around it to allow for romhacking. That could be nice. I don't know if maybe someone already did that, but who knows? And then kind of uncorrelated is what happens if I try to mimic maybe not the Game Boy CPU, but maybe an older one on Unity at electrical level. Lots of gates, lot of pain again, but that might actually be funny. And if by chance it works, and it works at a reasonable rate, let's say 4 hertz, that's her fault, because I saw her and said, oh, that could be nice also to do. Maybe trying attaching a tone for a different tone for every single wire that is going in and out, and see what happens if it plays something nice. Again, I could try and complete it on def, I don't know, and I don't absolutely guarantee any result. And that's basically it. So thanks for your attention.